Ladies and gentlemen, among the many things happening right now in the world of technology is a change in the way the machines that we use interact. It used to be the case that machines are purely things where you push a button and something happens, and we are now way beyond that point. And the upcoming speaker is giving you a very interesting view on one particular way in which the machines we're building are starting to interact themselves. Give a warm welcome to Frank Kargl.
Okay, so thank you for the introduction. Welcome all of you. Yeah, as Martin already told you, I'm going to speak about communicating machines, and in this case, machines means vehicles. We have some feedback anyway. And I'm going to talk about work that I'm carrying out at Ulm University about vehicular communication. So the idea is we make vehicles communicate with each other, and then a couple of nice applications are supposed to happen, and as I will point out in my talk, also some security implications will happen, and one of our work is about caring for that these systems are implemented in a secure way. There are also a couple of colleagues from me here in the room who also work on these areas, and I invite them and all of you to interrupt me anytime when you have questions, want to add some comments or whatever. So I don't intend to give a lecture like it's shown here, where I speak something like 1 hour or so. So whenever you feel the need for discussion or adding on what I'm saying here, just do so. Okay, so let's get started right away. Why do we want to have vehicular communications? Now, depending on the stakeholders, there are different motivations for that. From the academic side, it's surely that we want to get research grants, and some people working in that area want to make their PhD titles in that area. And besides that, I think I can speak for academia saying it's a cool subject, and this is why we're working on it. When it comes to the automotive industry, I think the main reason, of course, is they want to sell cars, and they want to sell more cars, and they want to sell more cars in the future. And today, it's the case that about 80% of all innovations in new cars is directly related to electronics, and in that case, mostly also software is involved. So in order to build innovative cars, they have to find new areas where electronics can be deployed, and vehicular communication is surely one of these areas. And, well, of course, the motivation behind it is if they have innovative cars, they can sell more cars and make more money out of it. I think for a commercial company, it's a pretty good or pretty valid motivation. And there's also a lot of money invested into that area of vehicular communication from governmental side, and their primary goal is to support active safety, to make driving more secure, to have less people get killed in accidents. And I think this is also a pretty good reason to look at vehicular communication. If you have a look at the slide here, starting from the 70s, you see we have a constant increase in traffic density in Germany. And if you compare this to the number of, let's say, severe accidents where people get injured or even get killed, you see that these figures are constantly declining. And that's obviously a good thing, and it's mostly, or to some extent, also thanks to electronics in cars. Things like anti-braking system, ESP, airbags, and so on, they all contributed to this trend. But at the same time, it becomes clear that these systems that try to mitigate the effects of an accident surely reach the peak of their effectiveness. I mean, you can put more and more airbags into a car, but at some point in time the whole car is filled with airbags, and then you can have additional effects by that. So what I want to say is that this area of passive safety that mostly deals with mitigating the effects of an accident comes, let's say, to some point of saturation. And this is where the focus gets shifted, and both the automobile industry and the governments and also the European Union try to focus now on so-called active safety. And active safety is everything that happens before the actual crash. So what can you do here? You can try to, for example, assist the driver in braking so that the accident or the crash gets less severe, and you only have a minor impact without any casualties. Or you can try to, let's say, prevent the accident at all. So that's the phase where the actual accident is about to happen, but for example, if you have ESP or something like that, the driver might evade that accident. And of course, the best thing to do would be to warn the driver in advance that there is a hazardous situation, and the driver simply can brake 500 meters before the end of a traffic jam or something like that, and then nothing happens. And this is where vehicular communication comes into play. So by making the car communicate either with other cars or with the infrastructure, the plan is to use this opportunity, this warning phase, to tell the driver, listen driver, we have an accident 500 meters ahead, slow down, and then everything is fine. Or even in an earlier phase, tell the driver, on your route there's an accident, just take a bypass or whatever. And this is exactly where these communication things come into play. So when you take all these electronic systems in cars, what we today have most often are these onboard systems like ESP that are vehicle immanent and just have information from inside the vehicle. For example, they can detect a crash and then set off the airbags or something like that. This is current state of the art. What's beginning to show up in high-end class cars are local sensors where the car gets information of its surrounding by radar or laser distance finding or laser range finders and so on. So the car gets some idea about its surrounding and can, for example, detect other cars that are hidden by fog or something like that. And this becomes also commonplace and will probably be installed into majority of new cars within the next couple of years. But again, these local sensors only give a very restricted horizon, very restricted information to the driver. It's about some few hundred meters at best. And what we now want to do is we want to extend this horizon of information getting to the driver almost infinitely, or at least to much greater distances, few hundred meters or even kilometers. And in that way, the driver here would get the information there's an accident here and can easily adapt his driving behavior accordingly. This whole area of e-safety is one of the application areas of vehicular communication. So I've depicted here some application scenarios. So what you can do, for example, if two cars have a crash or have an accident, local sensors detect this and just send warning messages via essentially wireless LAN to other cars. There's an accident at these coordinates. And once a car receives that, it simply can forward this message to other cars, and cars can be informed very early and prevent any further follow-up accidents. Another area where vehicular communication plays a role is the area of traffic management. So you can, for example, today you have these traffic sensors on bridges above highways where systems like Tegaron and so on collect data. But these sensors are relatively sparse. So what you can do if you make the cars themselves the sensors, they detect by ways of radar or by just measuring their speed where are local traffic jams, and then they communicate this via infrastructure, via roadside units to some traffic operations center, and this information is then disseminated to other cars, and by that you get a more fine-grained picture of the current traffic flow. So this is esteemed to really enhance traffic prediction, traffic monitoring, and to better control traffic flows so you have more efficient driving. And there are also other applications of wireless car communication in the, let's say, area driver comfort, entertainment. So you can, for example, have text messages sent from car to car. If you're driving in a group of cars, you can easily send messages without spending expensive short messages and so on. Or you can have media downloads and so on. All this becomes easily possible once you have these wireless communication technologies inside your car. And also car manufacturers envision that they can make their maintenance process more efficient. So you can, for example, have software downloads in the fields. You disseminate software updates to all cars without a need for them to get to a garage. Or when you have any problems with your car, you get automatic information, and the garage is informed, so they can already prepare the spare parts. So the idea is that everything gets faster, quicker, more efficiently here. So we have these 4 main areas of vehicular communication applications. The biggest and most important and where most research goes into is the e-safety area, where we try really to prevent accidents. But we also have traffic management, driver comfort, and maintenance. Actually, a list of potential applications is much, much longer. In our project, we have collected a list of roughly 60 applications that could be of interest in the area of vehicular communication. I just want to pick out some here to give you an idea what else could be done. So, for example, you could have traffic signs just sending information beacons to approaching cars, and then the car can calculate, is the driver going too fast, or is the driver approaching a stop sign too fast, and tell or send a warning. In theory, you could even go further and brake the car automatically, but this is another subject here. Or you can have cars approaching an intersection can exchange their positions and speeds and simply calculate would there be a chance for a collision at that intersection and warn drivers. Emergency vehicles could emit messages warning all cars in front of them to make way. Would also be quite easily to be realized. Vehicles could measure road conditions. So, for example, if you take information from ESP or other sensors on board, you can detect if there's an icy road, and you can then send this information to other approaching cars so they can be warned beforehand. There could be things like highway emergency system. If you are on a ramp and want to join on a highway, you get information about other cars. Where are they located? Are they in the blind spot? You cannot see them. And you get this displayed on some head-up display or whatever. You can send road surface conditions to some traffic operations center so they get a complete picture, for example, of road surface conditions and know where they have to do maintenance. Of course, you can also do things like area access control, that only permitted vehicles are allowed to enter some restricted areas, some docks or whatever. It's also envisioned to have software updating, flashing in the field. Of course, this poses some strong restrictions, or you need some strong control what software is actually installed in your car. I won't talk about that now. We will come back later to that in the security part. And so on. There's a long list. One interesting applications could be instant messaging. So if the car in front of you is driving too slow, in your opinion, you don't need to use hand signs and wave friendly, but you can send him a message directly. And so on. But you might have noticed today most of these applications are warning and assistance mechanisms. In theory, it will also be a potential for automatic reaction and driving. So for example, you could do this highway lane merging completely automatically. But for some very good reasons and not necessarily technical reasons, manufacturers and also researchers currently restrain from that. Because when you do automatic driving, you get a whole bunch of problems like user acceptance. Will users accept that their cars drive on their own? There are a lot of legal issues. What happens in case of accidents? Who is responsible, the driver or the computer? And also insurances will need to rethink their insurance models. There's a quite nice video. That shows that insurances are actually aware, at least, of these procedures.
Was wäre, wenn die Autos von morgen eine völlig neue Versicherung brauchen? Weil wir heute schon an morgen denken, können Sie jetzt und auch in Zukunft auf unsere individuellen Versicherungslösungen zählen. Zürich, because change happens.
Yeah, when I first saw this video, I thought, hey, that's cool, and you need a lot of technology to do that. Actually, I was wrong. We probably don't need technology for that, because I found another video. It's an intersection somewhere in India, and, well, I don't think they have all vehicular communication equipment on their bikes and cars, so it seemed to be possible also somehow else. Yeah, okay. Audio communication. But it seems we don't need all this technology. But I have some doubts that actually Germans would be able to participate in here. Could be a problem. Okay, so there are some local congestions. They need some more enhanced flow control, but I think it works pretty well. Would be interesting to see some statistics, how many accidents actually happen there. I guess so. Okay, so as I said, for some reasons, all these applications will stay within the warning domain. Automatic driving might be an issue in perhaps 20 years or so, but probably not earlier. As I said, there are a lot of stakeholders in this area, and there's a lot of interest and also a lot of research and a lot of research money invested in that area since a couple of years. That's also one of the reasons why it's interesting to work in that area, because I worked on ad hoc networks in a generic way before that, and there you're completely within your research domain and you make some assumptions, and here you really have to deal with the real world out there. There are standardization bodies, there is the question of frequency regulation, what frequency bands do you use. There are a lot of European research projects, also a lot of national research projects, past and present, that have delivered some first preliminary results in these issues. I will present most of or some of it during the rest of my talk. There's also already manufacturer consortium, the Car-to-Car Communication Consortium. It's not related to the Chaos Computer Club. But anyway, they are actually about to define standards, at least that's their mission, to define standards for vehicular communications. So the goal is probably to really have products with this technology in a time frame of 5, 7, 8 years. Because otherwise it would be useless to make standards already. Let's see what will happen. I assume it will probably take a little longer until you really see it. Yeah, then a lot of stakeholders that tell you, no, you cannot use that, and you cannot use all too expensive, and we won't build it into our cars. Also interesting. And also, as I motivated, legislation plays a role. What happens if your car emits false warnings and this leads to other accidents? A lot of interesting questions, not only for technologists. And actually, car communication, there have been early approaches already in something 60s, 70s, when you have a look at the cars. But actually, they weren't too successful, as you might imagine. So it was only about in the late 90s that when the wireless communication technologies has matured enough that people started to really research and look at this vehicular communication. So it's a relatively new field. And in this field, you find a whole bunch of different technologies. It's not only about communication from vehicle to vehicle, which is envisioned to be done by some flavor of 802.11, but you actually have a lot of other technologies involved. So you have roadside units that communicate by different means with the cars. This could be also radio, but this could also be infrared or something else. One plan is to equip road signs with communication capacities, message signs, but also to include all these other long-range communication technologies you see here, or hotspots, for example, when you are at the petrol station, long-range broadcast technologies for information dissemination like map updates in your navigation system. And of course, you also need localization mechanisms so that the cars know their exact precise location. So you also have satellite navigation, which plays a role, and so on. So it's a whole bunch of technologies that's involved here. I want to pick out some specific communication or some specific technologies that are especially important for this car-to-car communication. On the data link layer, as I already said, there should be there are currently plans to develop a flavor of 802.11, 802.11p, which is a modification of 802.11a, so it works in the 5 gigahertz band, and this should cover the data link layer, and to get better coverage, you also want to use multi-hop routing like in ad hoc networks or in mesh networks, and I will talk about these two technologies next. So when you go into this area, you see a couple of terms. One common term in the US is DSRC, Dedicated Short Range Communication, which both specifies the principle of communicating in short range by wireless LAN between cars, but also means a specific spectrum set aside specifically for vehicular communication. So the US already took a leap and they reserved these 75 megahertz. In Europe, there are still ongoing discussions about that, but in the US, this is already available for usage exclusively by vehicles. There's another set of standards subsumed under the under the acronym WAVE, Wireless Access in Vehicular Environments. This is a set of standards covering different layers. It includes 802.11p, but also addresses other issues. And this 802.11p is, as I said, a modification of 802.11a, which can be used for vehicle-to-vehicle or vehicle-to-infrastructure communication. One problem is that they modified they try to modify 802.11a as few as possible, so they can keep chip design and everything to build these devices cheaply. And as everybody who ever watched into the area of ad hoc networking and multi-hop ad hoc networking knows, especially the medium access, the MAC of 802.11 in general is not very well suited for these multi-hop communication. So this 802.11p really gets this bad, I would call it bad medium access mechanisms. But anyway, and this is one of these real world constraints where the manufacturers say it should be cheap. It can only be cheap if the chips are mass products, and mass products means stick with existing technologies. What actually, yes?
This might give some interesting opportunities to us hackers when we can use our WaveLAN card to speak with our car.
You probably won't be able to do this because it operates on distinct frequencies. So you would need some kind of software radio that you can tune to arbitrary frequencies. I'm not sure if current chipsets allow that.
Well, currently most of that is part of the firmware of the binary driver, at least at the WaveLAN B and G chipsets. Mm-hmm. And so it should be possible that at least some chipsets work on the P frequencies.
Yeah. Okay. I mean, the question was if one could use existing wireless LAN technology to interfere with these vehicular communications. I'm not completely sure about that. I mean, as I said, we have distinct frequencies, and I'm not sure if you can use the ordinary wireless LAN equipment and shift it to that frequencies. You probably need some software radio or so for that. Some information on that?
Basically, the problem is that, as you said, the Mac, which is for some cards implemented in software, like for Atheros, is not very well suited for mesh network or ad hoc. So one solution would be to rewrite this hardware abstraction layer and to maybe change this P standard into a fork or something that is much more suited to ad hoc mesh.
That would be.
But it's possible with current hardware that you can buy.
Yeah, sure. I mean, you can replace the Mac, but then it wouldn't be conforming to the standard, and there are no plans actually to change that for the standard. They try to modify the standard as few as possible, so I don't see this happening. Anyway, so what you have 7 distinct channels, 10 megahertz each, and you can also combine 2 channels to get enhanced bandwidth. So you get up to 54 megabit per second, like you do it with 802.11a. The interesting thing is that these channels have been separated for different purposes. So the central channel is this control channel where most of the communication, most of these warning messages, also beaconing messages and so on will be transmitted on. But using some still to be defined reservation protocol, you can use the control channel to set or to reserve these other channels for more bandwidth expansive communication. So for one idea would be if you for some reason need to download a file or whatever, you can try to reserve some spectrum here. The idea is that the control channel is only used for short packages or for short packets, so you don't block it for a longer time. Because another important thing here is with all these warning messages, we have a very time-critical applications. You cannot wait a couple of seconds until you send the warning messages, because then the accident might already have happened. So that's also interesting here. But as I said, some details are still missing. The current plans are to have this standard finished somewhere in 2008. So it's quite some work to be done. And what's also interesting here, you have different constellations. You might have high data rates with short range. You might also trade off bandwidth for range. So you might be somewhere here. And the communication class with the longest range, about 1 kilometer, using a directed antenna, is reserved for emergency vehicles. So emergency vehicles are planned to actually be able to notify one-hop cars up to 1 kilometer ahead. Now the other component that's important here is routing. So when you cannot reach the other cars directly, you do it multi-hop. And in that way, vehicular ad hoc networks are some special flavor of generic ad hoc networks. You might have heard of mesh networks, wireless sensor networks, which are some form of either static or dynamic multi-hop networks. There are other application areas for ad hoc networks, and one of the most promising areas of this technology that is around now for almost 10 years are vehicular networks. Whereas in these, or for most of these other networks, you use topology-based routing, where the nodes try to discover the logical topology of nodes and then build routes based on that knowledge. In vehicular networks, you do it a little bit differently. Let me give you an example. If you want to implement this road condition warning applications I spoke of earlier, you can do something like you have this car detecting the icy road, and then it sends a message to that car, and this message sends it to that car, and so on, and these cars get a display, icy road ahead, drive careful. That's essentially it. Sorry? Okay. And if you look at these scenarios, you find that they're a little bit different from what is looked at in generic ad hoc networks. You have very dynamic network topologies, simply because cars drive fast. So your topology changes all of the time, much faster than, for example, if you have networks consisting of pedestrians, or if you think of mesh networks, it's relatively rare that houses move, so you have nearly no mobility in there at all. Next thing is, whereas, for example, pedestrians move in a rather uncoordinated way, cars are usually bound to streets, so you have very different movement patterns that makes different classes of routing necessary. One problem that you don't have in cars is, for example, energy constraints. Normally with mobile devices, you don't want to waste too much energy because this would drain the batteries too fast. In a car, this is usually no problem because the car generates its energy constantly on its own. So there's a quite different setting here. There's another thing that's different. In normal networks, you have addressing modes like unicast, multicast, broadcast, and so on. You want to send messages to single nodes, or to a group of nodes, or to all nodes. That's essentially it. Any cast could be added. When it comes to vehicular networks, you usually don't want to send messages to a specific node, but with all these warning messages, with all these e-safety applications, you want to have some kind of position-based addressing. You want to send this warning to all cars approaching your current position, to all cars driving on the same street, or to a car that drives 5 kilometers ahead of you to request some information about traffic status. And this leads to new forms of addressing, like geo-broadcast. You want to send, for example, if there's an accident here, the cars here want to send messages to all other cars within the next 3 kilometers coming up this road. Or geo-anycast, you want to send it to simply one car in this area. And this has led to the development of new forms of routing protocols, so-called precision-based routing. One incarnation was found in the so-called FleetNet project that was done by Daimler Chrysler and others in I think up to 2003 or so. And they have two operation modes of this routing. When you are yourself inside this area, you can do some kind of controlled flooding. You just send the message to all neighbors, and the neighbors forward it if they are themselves within that area. So you simply flood an area. That's quite trivial. When you're not part of this area, for example, your car that's still 5 kilometers before that, and you want to send a message to that, you need an additional step, additional to flooding. You need to, some kind of line forwarding to forward that packet into that area. And the special incarnation of this protocol in the FleetNet project was called cached greedy geocast. This line forwarding mode works like follows. You specify a destination area where you want your packet to be delivered to. And another assumption is that each node constantly measures its position by ways of GPS or whatever, and periodically broadcasts this information to all of its neighbors. This process is called beaconing. So each node knows its own position and the position of all neighbors. And when it receives a packet that is destined to some remote area, it simply makes a routing decision based on these positions and tries to bring the packet nearer to the destination area. So, for example, here, if A wants to send a packet to that area here, it looks at its neighbor table, it sees there's B and C. C is obviously closer to this area than B, so it sends the packet to C. C might send it to D and then to E, and then this area is reached, so you have this path without any topology information. You just really look at the geographic positions here. This principle is also called greedy forwarding because you don't make any clever calculations. You just greedily forward it nearer to the destination, and that's it. There might be different strategies how to be what actually means closest to the destination. This depends on if you really want to get to have routes with as few hops as possible, or if you want to have to preserve energy and have routes where you send, for example, only on short links and so on. But I think for time reasons I will skip that. There are other problems when it comes to local maximum or local maxima when the message reaches this node here and should go from S to D. For that node, there's no nearer neighbor, so you need some strategy to get out of this local maximum. Different possibilities. You can try to get in a special parameter mode, no perimeter mode, that's wrong here, and try to use something like left-hand rule or so where you send it, or you can simply say, okay, cache it and wait for mobility to resolve this local maximum. And research has shown that this kind of position-based routing actually has a lot of advantages in vehicular networks. It naturally fits the way of addressing when you want to send packets to certain areas. And it also scales very well. So you have here some examples. You have simulations, and you see here the packet delivery ratio. And this line here is a specific topology-based protocol used in ad hoc networks named DSR. And you see when you have a larger area and vehicles are farther away, this packet delivery ratio here almost all packets get delivered, but then it declines quickly. And at the same time, position-based routing is able to maintain almost 100% delivery ratio. So, and also the amount, the overhead created by the routing process, by the routing protocol, goes up very quickly with DSR, but remains relatively small with position-based routing. So there are quite a lot of reasons why you want to have this position-based routing, and there's quite some consensus that this will be the kind of routing in vehicular networks. There are some drawbacks. You need a GPS, but you assume that future cars all will have navigation systems anyway, so this isn't really a problem. And there's a problem if you want unicast addressing. If you want to send a packet to a certain address, you first have to find out in what area that address is before you can deliver it. So you need some additional location service which creates additional overhead. So for unicast routing, it's not really perfect, but it is assumed that most of the applications don't need unicast routing anyway. I also have some ideas, but they are not really major to combine topology-based and precision-based routing. Anyway, yeah, but as we're here on a security conference, I also wanted to have some words regarding security and privacy. You remember these slides from the beginning of my presentations. Vehicular Communication seems to offer a lot of nice applications, a lot of opportunities for safer roads, vacant-one drivers, for more efficient driving, for more fun while driving, and for easier maintenance. So looks very promising here. Now, I probably assume at least 90% of you already has some ideas what else could be done with such networks. Will there really be safer roads if something like that can happen? Of course, I can just use my notebook. Either I have I have a software radio, or I might be able to buy such 802.11p equipment anyway, and I just send warning messages, and then cars start to break without any reason. Might not be so good. And more efficient driving, yeah, sure, but the question is for whom? I mean, if there's such a system, what I would do is I would send a lot of traffic update messages to this traffic operations center and saying, hey, at this location, or at this location here, there's a traffic jam. And then this traffic operations center would disseminate this information to other cars, and they would all use an alternate route, and then the route would be free for me. Would be very nice to have something like that available when you're a little bit in a hurry. Yeah, or could be interesting to see how drivers react if you send fake messages. Hey, there's a message from the silver car behind you, and this tells you you're an idiot. Could be that this leads to some interesting reactions of the driver here. Another problem is with privacy. If the cars start to send position beacons all the time, giving their identity and their position, people could try to track this information. Think, for example, of McDonald's or whoever, or some oil companies. They have a lot of stations around, and if they all have access points and simply collect these beacons, you can get a pretty fine picture of where are people driving when. And people give this information out for free. Yeah, and there could be a lot of more problems arising if you have such a system built in an insecure way. So, for example, think of software update. If I make it somehow to send false or faked software to a car, and the car actually starts using that software, it might be in the garage a lot faster than necessary. And I'm working in a project that actually deals with the security aspects and the privacy aspects of these vehicular communications. And for us, the first year now is over, and we spent most of the time of this first year looking into problems and attacks and threats, and find quite a lot of evidence that security is really needed here. So there could be, for example, attacks where cars try to modify the position they report in their beacons. So this car could send beacons telling everyone, hey, I'm here. And this could be used for black hole routing and for rerouting data, intercept data. I'm coming back to this on the next slide. And cars could even go further and send beacons for virtual identities. So they can do a so-called Sybil attack, where they create virtual presences or virtual copies of itself at different locations, and by that they might be able to control all the traffic that goes along a route. or they might impersonate other nodes and discredit other nodes, like I've shown here. So there's a lot of opportunity to mess around in such a system. One example, if you take some roadside attacker using his laptop, he could simply fake two positions, and by faking these two positions, they are relatively far apart, so that, for example, given position A here, or this car, if this car wants to send a message to D, then he receives the beacons from this notebook, and his beacons tell him, hey, there's a car here. So there's a lot of progress toward that destination area here by sending the traffic or the data, the packet, to that guy here. So this guy will be selected as next hop for all traffic coming down this road here. And in the opposite way, if you fake a position here, then car C, who receives this beacon from the notebook, will probably select the attacker as next hop for all traffic going in that direction. So with only two fake positions, yep, you are actually able to really capture all traffic on the road. And if you then simply, for example, drop the packets, we have done some analysis showing that you can bring down the efficiency of the network down to nearly zero with a single attacker. And if you if that you want to use these systems for e-safety applications and so on, this is clearly not acceptable. Because then if people start to rely on these systems, they will probably run into problems. This is also why you restrict yourself to warning applications, because if a warning application fails, you get no warning, but there's not a direct accident like when you have automatic driving or something like that. Here we also started to work on solutions for this. Some people suggest there's also work in the area to have to change the GPS or change the positioning system in a way that the car can actually prove that it's at the position where it claims to be. This goes in the direction of securing GPS, but the problem is here you would have to modify the satellite navigation system to support this. It's probably not something that even the automobile industry can enforce. Others suggest to have additional sensors that measure time of arrival, time difference of arrival. So you have onboard sensors that try to find out where are the other cars surrounding you. But this would mean additional hardware or modification to existing hardware. So would probably also be a problem. There's another way to cope with this problem of position faking. You can do something like using simply heuristics. By using a couple of heuristics, we have shown that you can relatively well find out if cars spoof about their position. So one very simple example would be some kind of acceptance range threshold. If this node here emits beacons telling everyone, hey, I'm at this position here, then these two nodes would simply find out, okay, if it would be at that position here, it would probably be out of communication range. So they simply disregard these beacons and drop it. And yeah, for these here, they wouldn't receive the beacons anyway because they are out of the actual communication range of that attacker here. And only a small percentage of nodes would actually believe these fake position claims. And by having such a very simple sensor, you can increase the delivery success ratio dramatically. This would be the delivery ratio if you have unsecured systems, and just by applying this very simple check, you get it up like this. And when you apply a couple of more of these sensors, this would already be quite good. Question?
Sorry, the last graph is Sorry, the last graph, is it from a simulation with circular transmission range?
It's with unit disk graph model.
Yeah,
Yes.
so because in reality, circular transmission range does not occur, and so
the problem here is that current simulation tools don't support realistic radio simulations. But currently, one of my students is working in his diploma thesis on some kind of extension to the simulation tools to have some kind of ray tracing, so you can actually model real situations, for example, from cities where have buildings that block transmissions and so on. But currently, these tools are not available, but we will surely redo these simulations with more realistic models as soon as they are available. Okay, so I'm running out of time. I will speed up a little bit. I already talked about the privacy problems when you emit beacons all the time. So, for example, these here are locations in my hometown, Ulm, where there are gas stations of a single brand. And you can assume that these cooperate, and they are placed on most major roads leaving Ulm. And if they have access points, they can easily track everybody who leaves Ulm. Just one company. So this would be a problem. The easiest way to evade this problem is that you don't use fixed IDs, but you change them regularly, use some kind of pseudonyms, and then you assume that the driver cannot, or that the attacker, the observer cannot link these different observations, these different IDs together. Whereas this is probably true in practice, there might be some problems with correlation of identifiers based on hardware fingerprinting, or some cross-layer issues that you don't change identifiers on all layers simultaneously, or there might be some guesses or some hypotheses about when a car enters the street and another car leaves the street and no other cars are around, it's probably that both are the same car and they just change the identifier. Another problem is that if you change your identities all the time, this leads to some problems with routing efficiency, because nodes disappear, other nodes show up. This might be a problem with the beaconing process. I am skipping that now. We analyzed this and we made a lot of nice graphs, but the essence is that if you change your identities too quickly, your routing performance goes down dramatically. Yeah, and this is the project I spoke of, Sevicom. You find information about that at sevicom.org. And as I said, the first year is over, so we have a good overview over all the threats and are now starting to really work on a security solution. And there will be quite a lot of components involved here. To prevent Sybil attacks, we look into a PKI for vehicular ad hoc networks, so you can really fix, or you can prevent nodes from creating arbitrary identities. You need some efficient revocation mechanism that works offline. You need cheap operation of this PKI. We need some anonymization layer. There are some ideas from IBM Zurich that could be used here. Especially, we think, or we have been told that pure anonymity wouldn't be accepted probably, but we need some kind of revocation mechanism in case there are accidents. Probably police or whoever would want to know which cars would be involved by simply looking at the beacons or so. Yeah, routing forwarding security, I already spoke a little bit about that, or these consistency checks, for example, on position, but also on other claims. So, for example, if a car claims icy road and other cars around tell you, oh, it's 30 degrees Celsius, there's obviously something wrong. We need in-vehicle protection mechanisms for protecting, for example, software update and so on. So it's a quite long list here. Okay, and this ends my talk, and I hope we have some few minutes for discussing especially the security implications here. So thank you for your attention. some questions here.
Thank you. Is there any transitional model from the actual to the one that you suppose? Because I will feel very scared driving my analog car to a crossing like this one with all cars talking to each other except to mine.
Yeah, actually there's a huge problem because you need a certain dissemination of this technology before it actually makes sense. So all of these warning applications doesn't help you if your car is equipped with it, but none of the other cars surrounding you is. There are calculations that you need some kind of about 5% dissemination of this technology to really get a significant benefit from it. And of course, car manufacturers and others think about how can you solve this problem. Some suggest you need regulations, you need laws. If you have laws that new cars have to have something like that built in, you would reach this dissemination rate within a few years just by having all new cars having this built in. Others suggest that you include or that you use these communication technologies, first of all, for other purposes. For example, for music download at your home. This is why you want to have it compatible with wireless LAN, so you drive in your garage and your car automatically connects to your home network and retrieves all the latest podcasts, and in the morning when you drive to work you can hear them. And once you have the hardware in the car, the rest is a matter of a software update. And you can do the software update as soon as you have this 5% or whatever. That would be another scenario for that. Okay, so we have 5 minutes left, so we do questions until the time is up.
Did you make any throughput calculations when you were using multi-hub routing?
There have been. I don't have the slides with me. I haven't done that myself, but this has been done by other researchers addressing especially the routing. As I said, I focus more or less on security. The bandwidth you will get is not too big, so you shouldn't be blinded by these 45 megabits. When you have multi-hop, you have this forwarding, you have this channel allocation problem. I don't have the figures in mind, but I look at my colleagues. Do they have? Tim, do you remember any actual figures?
2 megabit.
Sorry? 2 megabit. Based on 802.11a or b? A, okay, so you get a sustained throughput of 2 megabits, something like that, so it's not too much.
And latency?
Latency depends on how much traffic is there. But one of the problems is that you want to have the latency down to something like 100, 200 milliseconds, because you need, especially for the warnings, you need quick reactions. This is what they are currently trying to solve with this control channel in 802.11p. But I assume that as long as they stick with this DFW mechanism from 802.11, it could be a problem to give any timing guarantees here. So we'll probably have latencies in the area of second or something like that, depending on number of hops, of course, but rather long latencies.
Okay, thanks.
Do you know some company or country who are already deploying VANETs?
In the US, there are field trials. In the US, they are preparing a field trial on the West Coast where they want to have a couple of thousand cars, I think, included. Similar is underway in Japan. In Europe, there has been restricted field trials with, I think, some dozens of cars, but essentially that's it. In the US, they are pretty quick. They, for example, they also allocated, I think, $800 million budget for equipping every traffic light or most traffic light intersections with an access point. And in the US, they don't, as a contrast to Europe, they don't believe so much in car-to-car communication, but they want to realize most applications with car-to-infrastructure. So the intersections are equipped with an access point, and the cars communicate only with that access point. Makes some things easier, but prevents you from realizing some applications, because you wouldn't be able to equip all cars, all streets with access points, or to cover them completely. What you need, for example, for accident warnings or so.
I'm rather pessimistic about the security here.
Are you?
I'm here.
Okay.
I'm rather pessimistic about the security issues here. Compare it. I come with a comparison. Let's assume we build a system for the internet where machines can warn each other. Hey, there is a strange attack coming on. Maybe you'd better want to shut down your system, else it might get broken in. Would you trust some unknown machine telling you, hey, better shut down your system immediately without saving and such? I think we'd all want to disable this feature, and I'd also want to disable the feature some strange unknown supposedly vehicle on the road is telling me, hey, you better brake now because you might run into an accident. I wouldn't trust it.
I mean, if you have just a warning application, then you of course can double check. You can simply look, is there something? So it's more to focus your attention. If there would be automatic driving, of course the problem would be much more severe. Yeah, there's this whole area of cooperative security, and this cooperative, you would need some kind of reputation system that checks how reliable are your neighbors or the cars forming this network. There has been a lot of research in that area, a lot of simulations, but I feel that the viability of all these concepts can only be tested in real deployments. So as soon as the system will be there, I think there will be a lot of opportunity for testing.
That will be fun, and we have overpopulation anyway.
Well, okay, so is the speaker for the next session already here? Okay, so I think then we take the rest of the discussion offline and go outside.
Thank you very much, Frank Kargl.